My name is Garrett Gromes. It'd be much easier if I show my face at the end of the video the way my camera's set up. So here we have our three-dimensional combine loading problem. What we want to find here is we want to find the principal stresses and the maximum shear stress. So we're going to start off by doing is we are going to be finding the sum of the forces in each direction and the sum of the moments in each direction as well. And so at point H here, since we have multiple forces applied, we have a normal force here, which is going to be Nx. This is all going to be a moment force, or a moment 2. In the y direction, there'll be a shear force called that Vy. There's also going to be the moment there too. And in the z direction, there's going to be a Vz and an Mz. So finding the sum of the forces is the static objects is all equal to 0. So we're going to have this is going to be equal to our n of x minus the 3 kilonewtons, that right there, equal to 0. So I have nx equal to 3 kilonewtons. And then we're going to have our Vy, and this is going to be minus 0.5 kilonewtons, because that's force applied in the y direction, equals 0. So we make our Vy equal to 0.5 kilonewtons. And then we'll have our z, we'll have our Vz. This is going to be subtracting 2.5 kilonewtons here, so I have 2.5 kilonewtons. This is equaling 0. Solving for it, V of z will end up equaling 2.5 kilonewtons. Now, for the sum of the forces, in x direction, so we'll have m of x, there's actually no force that would try and make this object rotate along the x-axis, so this just end up being 0. For the y direction, we have our m of y, the force that's going to apply a moment along the y-axis is going to be this 2.5 kilonewtons. And so this is going to be applied in the positive direction, so it'd be plus 2.5 kilonewtons. And then this equaling to 0, we're going to have our, it'll be our 2.5 kilonewtons, but since the moment needs to be multiplied by the distance from the point H to the plane of the force applied. So this will be my plus 2.5 kilonewtons multiplied the 150 millimeters. This is going to end up being 375 Newton meters. Mz, whatever moment in the z direction. This force is, this one right here is making our force rotate along the z-axis. This can be minus, since this is making the z rotate in the clockwise direction. So it'll be 0.5 kilonewtons multiplied by the distance, which is 150 millimeters. This equals 0. Solving for this, we have mc equals 2. This ends up being negative 75 Newton meters. So now we have all of our internal forces, so we're going to see how each force applies a stress to point H. So we're going to start with our stress by our normal force. So stress by our normal force, if we were looking at point H from looking at it in this direction, we'll have our cross-sectional area look like this, where we have a force at the midpoint, we have our n of x, and we'll have our m of z right here. And looking at this, we'll have point H here. This is 0.02 meters, this is 0.04 meters. So the formula for finding our normal stress is going to be, the formula is our normal force divided by the cross-sectional area, and then it's going to be minus the moment of z multiplied by the distance from the forces to point H, which is this distance right here, which is basically half the height. It's going to be 0.01 meters. And that is all going to be all divided by the moment of inertia. The formula for moment of inertia is 1 over 12 base times height, so 0.04 times height cubed, 0.02 cubed. This is going to end up equaling, this equals, small number, this equals 2.66 repeating, so it's 2.67 times 10 to the negative 8 meters to the fourth. Plugging this all in, we have here, this will equal our 3 kilonewtons divided by, that should be 0.008 meters minus our negative 75 Newton meters times 0.01 meters, all divided by the 2.67 times 10 to the negative 8 meters to the fourth. And this number is going to end up being, calculator, this is going to end up being 24.37, which is, how many decimal places is that? 1, 2, 3, 4, 5, 6. Megapascals. So this is going to be our normal stress at point H. That's from our normal force here. And then so now we're going to be looking at our next one, which is in the y direction. Doing this, we're going to have our V of y, so stress by V of y. And looking at this with the cross-sectional area, at the midpoint here, the point H, and since V of y is actually running through point H, the stress caused by it is going to be 0 because there's no distance between the path of force and the point at H. So it's just going to end up being that there's no force. And then so I guess it would be force equals 0. And then so for our next one, this is going to cause, let's say, stress by, this is going to be our VZ. VZ. So looking at our sectional area here, stress by VZ. Here, look at point H. So over point H, I'm still looking back at this. So we have our point, I can cover this. Our stress from VZ is going to be here in this direction. And the stress that this causes is actually not a normal stress, but it is a torque because it is turning this. So it's going to be torque. And so for the formula for torque is going to be 1.5 times the force. So this is just end up being our VZ divided by the area. Area is still 0.02, 0.04 meters. So plugging this in, our force is going to end up being 1.5 times our V of Z is 2.5 kilonewtons, 0.5 kilonewtons, and this is going to be divided by our 0.08 meters. Plugging this into the calculator, we are going to end up with 1.5 times 2.5 times 10 to the 3 this should be 0.08, sorry. 0.008, oops. 0.008. So this is gonna end up being 468.750, and that is pascals. Or this is meters squared also, my bad. So it's gonna be 468,750, which is just gonna end up actually being, let's see, 4.6875 megapascals. Let's just call this 4.69 megapascals. And then, so that is the torque among point H. Now looking at the stress there's actually no stress from, no stress from our moment of the x direction because that's 0. Same thing with the stress by my. Here in our cross-section area, it's the same thing where we're looking at our stress from Vy. Our moment is still along this axis of point H, so it still runs through it, so this just ends up the force being equal to 0. And then Mz is our shear force that we had in this that we used right here. So therefore, the stresses that we have that matter in this problem are the normal stress. And that is because principal stress by definition is the normal max and normal minimum stresses. And to find normal max and normal minimum stresses, first we're going to look at the Moore's circle. And so basically what this is we're going to have our formula for max stress, and that's going to end up being our theta x over 2 plus the radius of the Moore circle. And to find the radius of the Moore circle, that's going to end up being r equals the square root of theta x over 2 squared plus the shear force squared. And in our case, that's just going to end up being r equals the square root of our, end up being the square root of our normal force, which is 2.437.4, r equals the square root of, I'll just do the hat later, 24.37 megapascals divided by 2. This is going to be squared, and it's going to be plus our torque here of 4.69 megapascals. And this is actually also going to end up being squared, all square rooted. Solve for this, our r is going to end up being, put this into the calculator, this is going to end up being 13.06 megapascals. Now plugging this into here, we're going to find our M max. Oh, and this is because looking at the Moore circle, I'm not sure if I have to explain this or not. Looking at the Moore circle, you're going to have your average stress, and then you're going to have your max stress, and then your minimum stress. And then this is just your distance r right here. And then so this is going to be our, normal stress plus r or normal stress minus r. So for max, it's going to be normal stress plus r. So we have our normal stress divided by 2 plus r. It's going to end up being, our value for normal stress is 24.37 megapascals divided by 2. This would be plus R 13.006 megapascals. Their max is going to end up equaling 25.2 megapascals. 25.2 megapascals. This is one of our principal stresses. Now to find the other one, which is going to be our stress min, this is going to end up equaling our normal stress divided by 2, except this will be minus r because we're going this direction of the radius of our Mohr circle. So this is going to end up being our value of 24.37 megapascals divided by 2 minus the 13.06 megapascals. This will be our stress min. It's going to end up equaling -0. Oh, I don't think I did that one right. Okay, so 24.37 divided by 2. 24.37 divided by 2 minus 13.06. Oh, okay, yeah. 0.874 megapascals. I didn't think it was going to be negative for pascals. So this is our final principal stress here. Now for the final problem that this was supposed to solve is for the maximum shear stress. So here we have the shear stress tau, and let's move this. Shear stress tau, and so basically we're going to find tau max, and all tau max is going to be is looking at our Mohr circle here. Tau max is just going to end up being this vertex right there. So basically that is just the value of r. So our tau max equals our 13.06 megapascals. And that is basically how you solve for both the principal stresses here, which principal stress is basically just the maximum minimum of the normal stress that we found. So that's why in the x direction, that's the only stress that mattered, or besides the moment z. And then this is just looking at the Mohr circle is gonna end up being our value of r here. So these are both our principal stresses and the maximum shear stress. And let's see my face. So that's it. Yes, this is my face. Have a good summer. Thank you.